In this video, we're going to look at converting from a 16-bit binary floating point number into decimal, and then going from the decimal number back into the 16-bit floating point number. Now we're going to use the number pi as an example. So the number pi is given by 3.14159.265,359, and it just keeps going. And we've seen from the previous video that we can use this equation up here. Now I've already gone ahead and I've generated the 16-bit floating point binary representation of pi, and that's given by this number here. So we've got 0 for the sign, we've got this 10000 for the 5 bits of the exponent, and we've got 1001001000 for the 10 bits of the mantissa. Now if you like, you can generate this number here using the tool which I showed you in a previous video. So this is the conversion tool, and we can put the number for pi in, 3.14159. That should be enough decimal places. We press return, we get the hex number is 0x4248. Now ignore this binary bit here for the moment, I have to fix that, it's not quite right. But the correct number is 0 for the sign, 10000 for the exponent, and then the mantissa is given by this bit here. So whenever we break it down, it will end up a value of 1, which is a positive number. We'll have the exponent, which will be 2 to the power of 1, which is 2, and then we will have the mantissa, which is 1.57, and it's a normal number. So we're going to see how we can go from the binary 16-bit float to the number pi, which is 3.14159. So we have three things that this number tells us. The first thing it tells us is the sign. So you can see here the sign has got a value of 0. So we put 0 into the first part of this equation. Okay, so I'll just put number 1 because that's the first thing that we're going to do. And we can see that the sign is equal to 0. So the equation tells us we write minus 1 to the power of 0. Now anything raised to the power of 0 is just a value of 1. So that gives us the value of 1. So it's obviously 1, so I'll just put the positive in front of it, so it's plus 1. So that just tells us that the sign bit is plus 1. So it's going to be a positive number. Now if that value there had been a value of 1, we would have minus 1 to the power of 1. Anything raised to the power of 1 is just itself. So if this was raised to the power of 1, it would be minus 1 to the power of 1, which is just a value of minus 1. And then we would have minus 1 instead of plus 1, and it would be a negative number. So that's the little mathematical trick for generating the sign using the first bit here, either a 0 or a 1. So that's us 1/3 of the way through. Now the next part of it is finding which box that we're in. That is, whereabouts in the range. So are we in box 1 to 2, 2 to 4, 4 to 8, 8 to 16, so on and so forth. And we get that from the exponent. So the exponent here is given by this number, which is 1, 0, 0, 0, 0. So that's 1, 2, 3, 4, 5 bits. Now whenever we work that out, that's going to be 1, 2, 4, 8, 16. So that's a value of 16. But as we said previously, in order to get the actual value, we have to subtract off the bias. Now the bias, as we said previously, is this number 15. So we've got to subtract the 15 off. And this gives us an exponent value of 1. So that means that we're going to have 2 to the power of 1. So the next part gives us 2 to the power of 1. So 2 to the power of 1 is just 2. So we're in the box from 2 to 4. And that's correct because we're dealing with pi. Pi is 3.14, so we're going to be in the box from 2 to 4. Now the final bit is to get the precision. Now in order to get the precision, we look at the mantissa. So the mantissa here is going to give us 1 upon 2. So I'll just write down the mantissa, I won't write the whole thing out. So the mantissa is going to be 1 upon 2, plus that would be 1 upon 4, 8, 1 upon 16, 1 upon 16, 32, 64, 128, plus 1 upon 128. Okay, now we don't just have the mantissa, we have the mantissa and we add 1 onto it. So we've got that whole thing there, and we add 1 onto it. Now I'm not going to go through the arithmetic, but you could work through that arithmetic yourself, and you're going to get a value which will look like 201 divided by 128. So we've got the three things that we need. The first part here is the sign, which is going to be plus 1. And then we multiply it by 1 plus m. 1 plus m is 201 divided by 128. And then we multiply this whole thing by the exponent value, and the exponent is given by 2 to the power of 1. So if we were to multiply all of this together, we would get the value, and you can try it in your calculator, 3.14065. And we can round this up to 3.141. So this here is our approximation to the value of pi to 3 decimal places. So it's a relatively straightforward method, and it becomes quite intuitive about what's happening whenever you think about it in terms of the range and the precision. The range is given by the 2 to the power of 1, so it tells us which box we're in, and the precision is given by the value for our mantissa, which tells us whereabouts in that box we are, and the sign is given by the sign bit here, 0 and 1. So that's a relatively straightforward conversion. So let's now go the other way. We're going to convert from our decimal number back into our floating point number. So now let's go the other way. We're going to go from 3.14159 back to the 16-bit binary floating point number that we have here. Now what we have to do is we have to convert this 3.14159 into what's called fixed point. So in order to get this into fixed point, it's simple enough to do the value of 3. So the value of 3 just has to be written in our binary. So binary for number 3, so the first part we could say the number 3 written in binary is going to be equivalent to the value of 1, 1. So that's 2 to the power 0 plus 2 to the power of 1. So that's 1 plus 2, which is a value of 3. Okay, so this is just written in our normal binary. Now, in order to do that, what we actually do if we were to do it by in longhand is we would say we would have the number 3, and if we divide the number 3 by a value of 2, then it gives us the value of 1. And we've got 1 left over, so we could put the 1 left over here. And then we could say 1 divided by 2. Well, 2 won't go in to the value of 1 here. So we've just got 1 left over, so we just put the value of 1 here. So we've just got the 1, 1, which is the value for our binary value for the number 3. Okay, so that's the actual little algorithm that you could work through in order to do this. Now, we have to get through a similar process in order to get the fixed point number for the decimal values. That is, let's say we just use 0.14159. So the 0.14159 in effect has to be written in terms of a summation of 1 upon the value of 2 plus 1 of 4, 1 upon 8, 1 upon 16, 32, 64, so on and so forth. So we have to try and find these values here that will give us this number. Now we go through a similar process as we did here, but instead of dividing we multiply. So the second part of this here, we're going to have another little table. So what we can do is we can take our fractional number. So let's just take a certain number of them. So we could go 0.14159, okay, and we can multiply it by a value of 2. So when you put that in your calculator, you get the value 0.28318. Now this value here isn't a value of 1, so if it isn't a value of 1, we can put a value 0 here, and we multiply again. So multiply that by 2 and we get 0.56636. Now again, this is not a value of 1, so we can put a value 0, okay? So that is it's a value less than 1, so we can put a value 0 here. Now whenever I multiply this by 2 again, we're going to get a value which is greater than 1, which is 1.13272. So this is a value greater than 1. So if it's a value of greater than 1, we subtract the 1 off here and we can put it there. And when we subtract that off, we're left with the 0.13272, and we go through the process again. We multiply this by 2, and again we don't get a value greater than 1. And if we continue with this process again, we multiply this by 2 again, and again we won't get a value which is greater than 1. And if we multiply it by 2 again, then we get a value that is actually greater than 1. and then we subtract off the 1, and in this point here we're left with a value which is 0.06176. Now we can multiply this by 2 many times, okay, so we can continually multiply this by 2, by 2, by 2, by 2, and we won't get any number greater than 1, so this is just going to be left with 0, 0, 0, 0. Okay, so this is the number that we're actually looking for. So we can rewrite this full number here in fixed point, and it's going to be given by, if I get space, I'll maybe just pop it over here. So it's going to be given by the 1, 1 for the 3. So we're going to have 1, 1, and we could put the decimal point here, and we can read all the way down here. So we're going to have 0, 0, 1, 0, 0, 1, and we'll have 0, 0, 0, 0. So this number here is going to be the 3.14159 in terms of a fixed point number system. Now we do something called normalization. So in order for us to have this in the correct format, this decimal point shouldn't be here. It should actually be in this position here. So we should only have one value here to the left of the decimal point. So this point here should float up to this point here. Now, if it has to float up just one position, then we can say that the value of e, which is the exponent, must be that value of 1. So e tells us how many positions the decimal point has to float in order to ensure we've only got one number to the left of the decimal point. So in this case, e is equal to 1. But remember, we still have to now add on the bias. So the bias is going to be plus 15. So that means we're going to have a value e, which is a value of 16. So that means that the exponent is going to be 16, which is going to be our 1, 0, 0, 0, 0, which is the exponent which we have above. Now for the mantissa, the mantissa is going to be, this point here has moved to this point here. Okay, then we're going to have this number 1.1001, and then 0, 0, 0, 0. Now, to get the mantissa, everything that's left of the decimal place, the decimal point, can be ignored. Okay, so this value 1 here is our hidden bit, and it's an understood. Okay, so in effect it works along with this 1 plus m. So whenever we generated it, we had 1 plus m. So in this case here, we're going to have to take the 1 away. So the 1 just disappears, and we're left with the mantissa, which is going to be our 1, 0, 0, 1, 0, 0, 1, and then we fill out the rest of the bits. So that's 1, 2, 3, 4, 5, 6, 7, that becomes 8, 9, 10. So this here is our mantissa. So we've got the final version, which is going to be a positive number, therefore it must be 0. And we've got the position within the range, which is given by the exponent, which is our 1, 0, 0, 0, 0. And we've got the mantissa, which is given by 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, so those are our 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's more to the process converting from the decimal number into the floating point number than going from the floating point number back to the decimal. But if you practice it a few times, it becomes kind of obvious what you're doing. And you can easily generate Python algorithms to do this for you. So we'll leave off the Python for the moment, and we can get that in a different video. So thank you for listening. I'll get you on the next video. Goodbye.